problem number 19 from Serway and Jewett, 8th edition. In this problem we have a knight wearing armor who's sitting right here, sitting on a horse, about 1 meter from the edge of a bridge. So the bridge is sitting at an angle like this of 20 degrees. The length of the bridge is 8 meters. The mass of the bridge is 2,000 kilograms, and the mass of this guy is 1,000 kilograms. We know that the distance between this point and this point is 12 meters, and that there's a line connecting between here and here. The first thing to find is what is the tension in that cable right there. Now, in order to do this, the first thing we need to do is to figure out what this angle is right here. All right? And the easiest way to do that is to draw a perpendicular to this line right here, from here. So that's going to make a right angle there. This angle here will be 20 degrees. This side, let's start with this one. This side right here, because it's adjacent to this, will be 5 times cosine 20. This side will be 5 sine 20. And we're interested actually in just now finding this angle here. Let's call that angle alpha. And we can say then that because you have a triangle here with the side, this side right here, which is going to be equal to 12 meters minus sine, or 5 sine 20. This side is this. We can say that the tan inverse of that side divided by this side and if you do that, you're going to get 65.5 degrees. All right. Now, in order to find the tension for part A, we can start off by applying the net torque equal to 0 equation. And we also need to identify what the forces we have in this problem are. So let's go ahead and do that. So this guy right here is going to exert a force here, which is equal to mg. At the center of mass of the bridge, there's going to be another force here, which is big little m times m sub b, g. We're also going to have a tension force pointing back this way. And in order for the bridge to be pinned right here, to have a hinge right here, it's going to have a vertical component of a force right here and a horizontal component of a force right here that I'm going to call r sub x down here and r sub y right there. Right? Now, if we choose for this torque equation this point to be our axis, we won't have to worry about those two forces. We'll just have this force, and this force. So let's start with this force right here. Torque is defined as the distance to that point, which in this case is going to be 4 meters. It's 4 meters just to this point right here. So it's going to be the force times the distance, the 4 meters. But we also have to multiply by the sine of the angle made between this radius vector and this here, which is this angle here. And since there's a right triangle here, that's 20. That means this is 70. And you're going to have to multiply this by sine 70. That's creating a torque that's causing the object to rotate in this direction. We're going to call it clockwise positive. We also have a torque from this guy right here. He's 7 meters from the end because he's 1 meter from this end. So since the whole thing is 8, 8 minus 1 is 7. And again, you also have to multiply that guy times sine 70 because obviously he's going to make the same angle here as that guy did. All right, so we get that right there for our clockwise torques. The only torque that's causing the bridge to go that way about this axis is this tension here. So we'll also get minus t times the distance that is away from the end, which is 5 meters. It's 5 meters from the axis to the place where it's attached. And we'll multiply that times the sine. We have to multiply by the sine of that whole angle right there, which is 20 plus alpha. It's going to be 85.5. Then we can solve this equation. This whole thing needs to be equal to 0. The easier way to do it, though, is just to add this one over there, which I'm going to do by putting this into an equal sign. All right, now we can solve for t. What we'll get for the tension. 27,714 newtons, which There's only enough sig figs in this problem to include those first 3 digits, but I'm just going to leave it like that for now. That's part A. For part B of this problem, we need to find the values of Ry and Rx. And in order to do that, what we have to do is to use these 2 equations. Net force in the x direction equals 0. We use that one first. There's only 2 forces pointing in the x direction in this problem. You've got Rx. And in the other direction, we've got Rx points this way. This t right here is going to have a component that points this way and a component that points up this way. The bottom component here is going to be t cosine of alpha. Okay, so if you plug that value for t in, take the cosine of 65 and multiply by it, what you'll get is 1, 1. Like that. That's going to be the s component of that reaction force. And then if we use net Fy equals 0, we're going to have Ry equals this plus this minus this component here. Like that. And if we calculate that by plugging in the values, we get 4189. Now if you're trying these numbers here, and you don't exactly get that, it's because I've actually included, if you do this calculation here, you'll get 65.45 with a bunch of other decimal places. So I've included that precision in that number, which leads to this right here. But if you try these, you should get roughly close to the same.